Okay. All right. Fundamental theorem of line integrals. All right. First of all, I have to preface this by saying there's a lot more theory to this than I have put up here on the board. It is in your book. Okay. But basically, the fundamental theorem of line integrals says if C is a smooth curve given by a vector function R, where t goes from A to B, and f is a differentiable function of 2 or 3 variables whose gradient vector is continuous on the curve, then the line integral over C of the gradient vector dot dr is f of r of B minus f of r of A, which means that you can evaluate the line integral of a conservative vector field simply by knowing the value of f at the endpoints of your curve. A conservative vector field is the gradient of a potential function f. I'll give you a minute to write this. Or if you want to underline it, it is in your book. On page something.
1127.
Thank you. 1127. It is the theorem 2 and the note right under it. Page 1127. Give you a minute to write that. Okay, in the previous sections, when you had a curve, C, you had to find parametric representation for the curve. And you had to get the direction that goes from A to B. So you had to follow this curve. You had to know an equation for it in parametric form. If your function here is a gradient vector, then it does not matter about the curve C. You do not have to find a parametric equation for C. All you have to know is the value of the function f at these two endpoints, which makes your problem a lot easier if this is a conservative vector field. Ooh, I'll try. It may not be the same words, but I'll try it again. Okay. In the past, 16.2, okay, when you had a line integral, oops, I'm going to move this a minute. If you had a line integral over a curve C, right here, that went from A to B, and it went from A to B, you had to know a parametric representation. You had to know x was h of t and y was g of t, and you needed to know that t went from A to B, and you had to change everything to t's. Okay? If, and well, this was the integral. Let me go back to this. This was just some random vector field f. Okay? Just any old vector field out there. You have to get a parametric representation. In this theorem, this function right here has to be a conservative vector field, and we're going to find out how to see if it's conservative. If you have a conservative vector field, then you no longer have to worry about the path getting parametric representations. All you need to know is the value of the function at this point and this point, and you subtract them. You don't have to go through the parametric forms if this is a conservative vector field. Now, if this is not a conservative vector field, you've got to go back to the old way. Did I do any better that time?
It's fine the first time. I just wanted clarification.
Yeah, I just wasn't sure if I
think
said
it
it.
was the conservative vector field threw me off, and I was expecting like an explanation of what it was.
I'm going to show you what a conservative vector field is in a minute. Okay, a conservative vector field basically means that it is the gradient vector of a potential function f. Now, potential function f, this is actually going to go back to something we did in DE. Yeah. Do you remember in DE where we had exact differential equations? All right, I know you remember the words. All right, and you had the partial with respect to x here, partial with respect to y here. You did some integration, some manipulation, and you went back and found the function f. That would be the potential function. That's what we're going to be finding today, is the potential function. We're going to use the methods from differential equations that we did to go backwards. Okay? I know. All righty. And this also, another consequence of this theorem is that the line integral of a conservative vector field is independent of path, which means it doesn't matter if you're going from A to B. If you have a conservative vector field, it doesn't matter if you go along path C1 or if you go up here along path C2. It does not matter. You will get the same number if your vector field is conservative. Again, this is where the other theory comes in. The vector field's got to be closed, it's got to be simply connected, it's got to be all this other stuff. For our purposes, we're going to assume it is all those things. All right, this is what we're going to do to tell if something is conservative, if our vector field is conservative. If you have a vector field, P I hat plus Q J hat, if the partial of P with respect to Y is equal to the partial of Q with respect to X, then our vector field is conservative. And you can use this theorem. If it's conservative, you have to go back and find function f to use the theorem. And I'll go back through all those steps. Okay. This is number 3. If you have f of xy is equal to xy plus y squared I and x squared plus 2xyj. It's number 3, I think. It's close enough anyway. They want to know, do what? Oh, that's, oh, okay. All right. They want to know, is this a conservative vector field? Okay, to see if it's conservative, you're going to do just like you would in DE if you were trying to see if this were exact. You're going to take the partial of, I'll just call this P with respect to Y, which is going to be x plus 2y. You take the partial of this Q with respect to X, that's 2x plus 2y. You look at these, if these are exactly the same, it's conservative. This one is not conservative. So if we were using this as an integral, we would have to go back to the original method of working an integral. It's not exact, so it's not, it's not conservative. All right, let's look at one that is conservative and remind yourselves of how to go backwards and find your potential function. This is number 4. F of xy is y squared minus 2xi plus 2xyj. I think this is conservative. All right, so let me check the partial of p with respect to y. That's going to be 2y. The partial of q with respect to x is also 2y, so therefore it is conservative. So now, if I were going to use this in an integral, I would have to go back and find my potential function. All right, this is where we're going back to dE. By definition, this has to be the derivative of a function with respect to x. So this is the partial of a function with respect to x is equal to y squared minus 2x. If you integrate this, then you're going to get a function. You integrate this, you get f. Integrate with respect to x, you get xy squared minus with respect to x, 2x squared over 2 plus some function of y. So f so far is xy squared minus x squared plus some function of y. Now what we did is take the partial of this with respect to y. Partial of this with respect to y is 2xy plus g prime of y. And we're going to compare that to this part of the equation right here. We're trying to find what g of y is. These are the same. That leaves g prime to be 0, which means that g of y must have been a constant. So the potential function f, that means g of y is a constant, so our potential function f is xy squared minus x squared plus a constant c. Oh, and I forgot to look and see if WebAssign wants that c. What about it, Bailey? No, they do not. Because they list it as a function, they don't want the c at all. Don't put it on there. But we did in DE. Does this look familiar?
So does it always have to be 0 for it to be C, or just any number?
It would always be any constant.
Any constant. It would just be a C.
Well, this is always going to be, this will be a 0, or it'll be another function where you have to integrate to get back to y.
Okay.
Yeah. Okay, do I need to do another one of these in 2 variables to go back over it? Because I need to show you how to do one with 3 variables. We didn't even do that in DE. Okay. Actually, we don't even learn how to do this part until a few sections later. They're going to give you a function of 3 variables, and they're going to say it is conservative. Go back and find me the original function f. Okay, so we're not going to be testing those for conservative. Does that make sense? Until a few sections later. So in a problem like...
Would it be the same method?
No, it's a little bit different. Because you could, this method is the same. This is not.
Okay.
Okay, does that make sense?
Yeah.
This method is the same.
Right.
But this finding whether it's conservative or not is not the same. Right, because you've got that third variable in there, z. Yeah, you've got that third thing in there, z, which is like, yeah. But let's just go through this method. Let's say you've got a function f of x, y, z, and it's equal to y, z, I plus x, z, j plus xy plus 2z Okay. It is given on this problem that f is conservative. We don't have to show that. But since it's conservative, you've got to be able to go backwards and find your original function. Start off just like before, okay? This has to be the partial of the function with respect to x. If you integrate this with respect to x, then you get f is xyz plus. Now this time, it is not just a function of y. It is a function of y and z, because you've got that third variable out there. Now I'm going to take the partial of this with respect to y. Partial of this with respect to y is xz plus, when you take the derivative of this, you are taking the partial of this with respect to y, because it's not just a prime anymore, it's got two variables, and you're comparing it to the second term here, which is xz. These match. That means g prime of y is equal to 0. That means you took the derivative of something and you got a 0. Now it might be a constant, but it also might be a z. It just didn't have a y in it, because the derivative of z would be a 0 if you're taking it with respect to y. So this might be, g of yz might be a function only of z. We don't know if it's a constant, we don't know if it's a z, we don't know what it is. So right now what we've got, after all this, we've got f is equal to xyz plus h of z. So we've taken care of the first two parts of this. Now we need to look at the third part. So now we need to look at the partial of this with respect to z. The derivative of this with respect to z is xy plus h prime of z. Compare it to the third thing in this problem. I'm comparing it to xy plus 2z. The xy's match. So h prime of z must be 2z. If you go backwards to get h of z must be 2z squared over 2 plus a constant c. They don't use your constant c in here, so we can drop that off. But the h of z must be z squared. So if you take that and put it back into your function up here, right here, your function f is x, y, z plus z squared. That's your answer. Okay, is this sort of making sense with what you know from DE, going backwards? All right, now let me put all this together in a problem where you're doing a line integral. Okay? Do what? Oh yeah, you forgot about that? Yeah, that's the reason we're doing all this. Okay, let's look at a problem. Let's look at number, I don't know what looks good. Let's just look at number 12. All right, 12 says that f of xy is 3 plus 2xy squared I plus 2x squared yj. And c is the arc of the hyperbola. Y is equal to 1 over x, and it's going from 1, 1 to 4, 1, 4. And we are looking for the line integral f dot dr along the curve C. Now, if you were doing last night's homework, you'd find a parametric equation for this. You'd substitute it in your line integral and you'd do all that stuff. But that's not what we're using today, okay? We're going to see if this is conservative. So, look at your partials. The partial of p with respect to y is 4xy. The partial of q with respect to x is 4xy. Therefore, it is conservative. So now find your function f. So go through all those steps we did a minute ago. The partial of a function with respect to x is 3 plus 2xy squared. Integrate. So f is 3x plus 2x squared divided by 2, so that's going to be x squared y squared plus a function of y. Take the partial of this with respect to y. That's 0. This is 2x squared y plus g prime of y. I'm going to compare it to 2x squared y. That means g prime is 0, which means that g of y is just a constant. Therefore, your function f, the one you're going to need in your problem, is 3x plus x squared y squared. Everybody with me to that point? Now, the theorem that we use tells us all we need is f of this point minus f of the other point, from endpoint to endpoint. This is your function f, so all we need to do is do f of 4 1/4, find that, find f of 1 1, and subtract them. So let's 4 1/4, that would be 12 plus 16 times y squared 1 over 16. Is that 13, maybe? It's 12. Okay, so that's 13, and I got a 4 there, so that would be 13 minus 4. The value of the integral is 9. That's it.
So for all of these, if we get C, just drop it.
Just-
Because we're actually evaluating it at point.
Yes.
So is that why you didn't have it in the function? Did you just drop it?
Is that why this? The reason I could drop it is because this is conservative.
Okay.
Okay, if this had not been conservative, I would have had to go back to the method that you used in 16.2. Find a parametric equation, do all your substitution, and evaluate your line integral. Okay, it's conservative, so it doesn't matter your path now. Whatever path you choose, as long as you know the endpoints, that's all you need because the field is conservative. Okay, do you want me to do another one? Anybody? Eddie, what's your question? You look like you're mulling something over.
Always know.
You're always mulling. Okay, you can always mull.